Hey, let me share with you a very interesting problem that I've come across, and it has bugged me for 3 days now. Now, this problem is an age-old classical physics problem, and it involves the use of derivatives. Now, as we all know, derivatives, by their notion, essentially, it just measures how a function changes with respect to its input. Now, the problem goes as follows.
Suppose you have a ladder 7 meters long leaning against a wall. If the bottom of the ladder is pushed horizontally toward the wall at 1.5 meters per second, how fast is the top of the ladder sliding up the wall when the bottom is 2 meters from the wall? Now, because of the way it is phrased, it might be a little harder to comprehend the problem. But if you think about it, when we ask how fast does the top of the ladder slide up the wall, we're basically just asking how does the length of this leg right here change over time. Now, of course, we can simply work out the Pythagorean theorem here and get ourselves the length of this leg. But remember, the problem specified that each second, the length of the base decreases by 1.5. So now, it seems like we have two variables that affect the length of this leg. That is, the time and the length of this base. To keep this easy, let A be the distance from the bottom of the ladder to the wall. Let B be the distance from the ground to the top of the ladder, or basically the height. And let C be the length of the ladder, which happens to be 7 meters. Now, what's really interesting is if we assume this system is a right triangle, we can work out a lot of math from here. Now, by the Pythagorean theorem, we can say that a squared plus b squared is equal to c squared, or in this case, a squared plus b squared is equal to 49. What we want to find is how b changes over time, or dB over dt. And looking back at our equation, it doesn't seem to be the case that, independently, b is a function of a or a is a function of b. No. What this equation represents is just a relation between a and b that satisfy this condition of being equal to 49. Now, first, if we disregard our derivatives and think about this with common sense, 100% surely, b will change when a changes because of the Pythagorean theorem. However, a changes over time. So, if a changes over time, then it must be the case that b must also change, since b depends on a. So, by that, we can say that b is intuitively a function of time t. Hence, why when we look for dB over dt, we don't simply just differentiate b in terms of a, but we use the chain rule since a is essentially a function of t and a is being used in finding b, which is basically a composition of functions. So, going back to our original equation, a squared plus b squared is equal to 49, we can solve for b in terms of a, and with some algebraic manipulation, we get b equal to the square root of 49 minus a squared. By the chain rule, dB over dt must be equal to the derivative of b with respect to a times the derivative of a with respect to t. Substituting b for the square root of 49 minus a squared, we get this form. Now, how can we find the derivative of a with respect to time t? Of course, we can make our model for a with respect to some t seconds as a function. However, it rather seems obvious that this is already in the problem. So remember, when we push the bottom of the ladder to the wall 1.5 meters per second, this basically means a gets smaller over time. So it must be the case that dA over dt, or the derivative of a with respect to t, is simply just negative 3 halves or negative 1.5 meters per second. Furthermore, on our differentiation, we can apply the chain rule once more to simplify the derivative of the square root of 49 minus a squared with respect to a. Basically, we multiply the derivative of the outer function with the derivative of the inner function so that the derivative of root 49 minus a squared is just 1 over 2 times the square root of 49 minus a squared times the derivative of 49 minus a squared. And with a little algebraic simplification, we get down to 3a over 2 times the square root of 49 minus a squared. Since we know that a is equal to 2 from the given, we can simply substitute a equal to 2 to find dB over dt. And by doing so, we get dB over dt, or the derivative of b with respect to time t, equal to the square root of 5 over 5 when a is equal to 2. Therefore, it must be the case that the top of the ladder slides up the wall by square root of 5 over 5 meters per second when the bottom of the ladder is 2 meters from the wall and is being pushed 1.5 meters per second to the wall.